So we're group 12. We've got the solar power cooling system. So we've got the AI cooling system. We've essentially got solar panels, a battery, and a fan to cool an AI solar center, power center. For the solar panel subsystem, we've got parameters. The main thing to note here is we've got four different options for types of panels, and they all each have their own parameters listed in the table on the left. And go to the next slide. The design variables, we got M, which is the number of panels in series within a string, and then N, which is the number of panels in string in parallel. We've got constraints listed on the right, as well as derived intermediate variables on the bottom left. For the objective function, we've got to minimize essentially M times N times CP, which is the cost per panel, times the number of panels M and N. Go to the next slide.
All right, so for mathematical modeling, this is a constraint integer nonlinear programming model where we have, as Austin said, two design variables that are integers, and we got a couple of constraints here between the system voltage maximum and the load minimum, so that we go through the iteration to create our intermediate variables, and using the genetic algorithm are able to determine what are going to be our population that go through the genetic algorithm and give us what's going to be through multiple iterations our best option for our optimal design.
So for our optimization method, we use MATLAB because we were most familiar with it. We tested different functions in MATLAB, and it turned out genetic algorithm was the best option because it was best for integers and for nonlinear problems. Its stochastic nature did lead to slightly different panel combinations each run, but it's turned out to be the best one. Our algorithm essentially runs the cost for each panel output, and then chooses which one to have its lowest cost overall.
So for different iterations, we're able to look at that stochastic nature as well as we were manipulating what are going to be the inputs. We noticed the outputs changed slightly on the objective function, but the number of variables for sure did have different numbers. However, each one of those runs did show us that the design chosen number two was going to be the best one for our system. So next up is going to be the fan subsystem.
The fan optimization model is a heat transfer problem that relates the input wattage from the other two subsystems ultimately to the RPM of the fan, and using that in the outlet area finds airspeed, which then considers the maximum temperature allowed of the processor surface to calculate the heat transfer. It is a nonlinear program with real numbers, constraints by only side constraints, as well as a time limit for how much it needs to cool, and the Reynolds number, which dictates that the flow is turbulent. Next slide, please. Some of the important mathematical steps was first a benchmark. Notably, this problem could have been a genetic algorithm problem, but we wanted to mathematically relate the wattage of the fan to the airspeed to its approximate cost. So we took these benchmarks, and next slide, we fit a line of best fit through it to develop our cost equation. Next slide. And then we used this setup here, which is a fan that blows across 20 racks with 10 CPUs, each in a row. And we model them as flat plates. Notably, the Nusselt number is also simplified because a more rigorous CFD would be required to fully capture the heat transfer. So this is considered a worst case or least efficient heat transfer optimization model. Next slide, please. So ultimately, the results were that the fan wattage was kept as a constant for now, since that is in the scope of the later half of this project. The ideal temperature was varied because the biggest driver in a heat transfer problem is temperature difference. And of course, if you look at run 3, a smaller ideal temperature required more heat transfer, thus higher RPM and higher cost. Lastly, runs 4 and 5 varied the starting guesses, and it converged to the same point, which indicates a relative stability of the F-min-con, which makes sense. And it also showed that this might be overly constrained if this were a real-world problem, because the maximum processor temperature hung out around its minimum allowed, and the ideal temperature couldn't be less than 342 K without becoming completely infeasible.
Yeah, so for the battery subsystem, in terms of design variables, we have four things that we're looking at. So we have the number of cells in series, in parallel, and then the capacity of the cells. And something that impacts each of these is the battery type. Then our main objective here is to minimize the cost of our battery system. Some of our constraints and parameters lead into trade-offs. So the obvious ones here are, more cells leads to more capacity, but also higher cost and it takes up more room. And in between, we use several intermediate variables. Next slide, please. So for the mathematical modeling, our methodology was basically identify four potential battery types with LFP or NMC chemistry, and then cylindrical or prismatic forms. Then other data from the spec sheets, which led to us identifying basically how the cell capacity related to things like cell resistance, volume, and the big one, cost. We then generated equations to map these relationships. The necessary assumptions here, expecting our data to be an accurate representation of the battery types and that these equations are properly representing the relationships. Next slide, please. So here is just one quick example. We did this for all four battery types, but this is for the LFP cylindrical. So you can see the three relationships I just mentioned, along with an equation which ties things together. Now we can go to the next slide and pass it over to Mark.
An open circuit voltage resistance model was used. Power balance was used to calculate the max current and average current, and this was used to size the cable. And energy balance was used to make sure the full battery capacity was meeting the requirements. Next slide. Because the number of cells in series and parallel are integers, and this is a non-linear problem, genetic optimization was chosen, each battery type was optimized, and the lowest cost was chosen, as seen on the next slide. The top table here shows the optimization results for all four batteries, with LFP prismatic being the cheapest. The optimizer was repeated 3 times, and while LFP consistently came out the cheapest, the exact number of series and parallels could vary. This is because once the optimizer gets close to the right number of parallels, the cost difference becomes very small, making it hard for the optimizer to land on the exact spot, but everything's within 5.5%, so they're still doing a good job. Next slide. Finally, we looked at the impact of adjusting the scaling of MATLAB's fitness function. The default method uses rank scaling, which scales the fitness scores by rank. Next, we ran proportional scaling, which did a comparable job. The last 3 use top scaling. This applies to equal scaling to the top of a given percentage. The rest of the population cannot become parents. When 5% was used, the initial strong candidates overtook the gene pool, preventing the full solution space from being searched, leading to a bad result. 40% worked well, but 90% was too broad.